page 140, 141, because I didn't print short notes, but I can give you the excerpts from where you can see this proof, but I will explain it in slightly more simplified way, and I will begin. So, there are two statements. First, if we have a self-similar set, I will show you the page in larger size. This way. Yes, if you have a self-similar set, he has different notation. Yes, for his self-similar set is fractal, so he denotes by F. Yes, and if the open set condition holds for these self-similar sets, then Hausdorff dimension and box dimension coincide with the similarity dimension of this system. And moreover, for this value of S, Hausdorff measure is positive and finite. So I will do all this job, explaining and showing you the pictures. So one part was shown initially. So if you have K is equal to union of Si of K, then if K is union of Si of K, then for any delta, the sets Si1 In of K, where I1 In are chosen such that Q I1 In is less than delta, less or equal than delta, and Q I1 In minus 1 is greater than delta, then this set form a delta covering of K. Yes? Oh, sorry, maybe I will do it in slightly different way, because this choice will be made where N is chosen such that Q maximal to the power of N is less than or equal than delta. So I will make them of different size, but all the sizes of these copies will be, so I take, in the case when the copies have different size, I will take such N that the largest nth iteration of the largest copy is less than delta, so all these copies will form a delta covering of K. These sets form a delta covering of K. Therefore, the sum, so let S be the similarity dimension of K of the system S. System S. It means that Q1 to the power of S plus Qm to the power of S equals 1, right? Then the sum of Qi1, the sum of diameters of Si1 In of K to the power of S will be less or will be equal to diameter of K to the power of S multiplied by the sum Qi1 In to the power of S, but this sum can be transformed in the way that it will be K to the power of S multiplied by Qi1 to the power of S plus Qm to the power of S to the power of N, right? And this sum is equal to 1. Therefore, we have for each delta covering, there is a delta covering of K such the sum of diameters of the elements of delta covering to the power of S is less than so the sum, yes, is equal to the K to the power of S. So we have a delta covering of K, yes, and the diameters of the elements of delta covering, when we take S power of these diameters, sum up to Ks. But what can we say about Hausdorff dimension? Hausdorff dimension. Hausdorff dimension of S of K is a do you remember how we define the Hausdorff dimension? We take Hausdorff measure or Hausdorff content, and we take the minimal number for which Hausdorff content is equal to 0. Yes. But if this sum is equal to Ks, then Hausdorff content is more or equal to 0. So the dimension of K should be less than S. Yes. So from that it follows that Hausdorff dimension of K is less or equal than S. So this thing I already explained, and it is quite simple. But we need to prove the other inequality, that Hausdorff dimension of K is greater or equal than S. Can I continue? So, you see, I just repeated this excerpt because I explained it earlier, and it doesn't use the open set condition, but we need to use the open set condition. Yes, it will be the argument showing that Hausdorff dimension of K is greater or equal than S. Yes, needs more. First it appeared in Hutchinson's paper, Fractals and Self-Similarity. Yes, and this way of thinking became classical. And I will explain it. So I proved the other side, yes, the other inequality. Let S satisfy the open set condition. Not long ago, I explained to you the mass distribution principle. The mass distribution principle. So if, how it sounds, it sounds the following way. If there is mass distribution principle, looks the following way. If there is a measure on X, such measure, positive finite measure, such that mu of x is not zero and is less than infinity, and it is, for example, equal to some m. Yes, and for any ball BR in X, the measure of BR, oh sorry, this, okay, measure of BR is less than CR to the power of S, is less or equal than C are for some constant such that mu of x equal to m, and for any ball Br of x, mu r of Br is less or equal than c multiplied by r to the power of s, then hs of yes, hs of x, sorry, I forgot, is less than what? I don't hear. Yes. Is hs of x is more than mu of x divided by c. Yes. Okay. Hs of x is more than mu. So I mean mu of x divided by c. Okay, therefore, since the Hausdorff S-dimensional Hausdorff measure of x is more than mu of x divided by c, then the dimension of x is again I'm mixing. If mu of x, hs of x is more than m, the dimension of Hausdorff dimension of x is so we have opposite. Here we had less. Okay, then Hausdorff dimension of x, Hausdorff dimension of x is, greater than s. Greater than s. So this is a mass distribution principle, and we will base on this mass distribution principle and open set condition to prove that Hausdorff dimension of x is equal to s. Okay. I want to say several words about open set condition. Can I erase this part? Okay. I want to say some words about the open set condition. So if the open set condition is satisfied, then we have such an open set O that Si of O lie in O and they don't intersect. This we know very well. Yes. So if we have, so for any I not equal to j, Si of O intersection Sj of O is empty. If we take any family of tuples Si1In and if you have two tuples Si1In and J1Jm such that they are non-comparable, it means that this is not a prefix, first is not a prefix of second, and second is not a prefix of first. Then if are non-comparable, then Si1 In of O and Sj1 Jm of O will have empty intersection. So if we have these sets, then we have this sets second iteration of V of O, and further all these sets have the only relation: either one lies in the other and the multi-indices are comparable, or they don't intersect. Therefore, we can consider very interesting families. How to call it? Given a number rho more than 0, we can consider a family of such multi-indices I1, In, the n may be different, such that Q I1 In is less or equal than rho, and Q I1 In minus 1 is greater than rho. So what does it mean? What does such family means? We have copies of different size, right? So the size of these copies is, suppose that the diameter of K is 1. So we consider only those copies whose size is less than rho, whose diameter is less than rho, and their previous ones, when we truncate this number, are greater than rho. So they are approximately of the same size. So we consider such family. And further works also use these families. And in terms of these families, the weak separation property is also formulated. Okay. Maybe I will denote it by Q rho. So if I consider this family, we have one very interesting relation. So rho Q I1 In is less or equal than rho, and from the other side Q I1 In is greater than rho multiplied by the minimal Q, right? So from this definition of this family, for each of these elements we have the following relation. This is the first. Second, very interesting, if we have any of elements of this family, then they are not comparable, yes? Because if we have some element, we have some multi-index, then its prefix doesn't come to this family, right? So for any two elements qi1 im qj1 j i1 in qj1 jm, these two elements will be elements, elements, excuse me for my pronunciations. These two elements will be not comparable. First, all indices I1, In in Q are not comparable. At the same time, we have that K is equal to the union of SI In of K, where I1, In belong to Q rho, right? Because for any copy, so if we take any point, then it is the intersection of nested copies, yes? So it will be QI1, QI1I2, QI1IN, right? And in this sequence, there is only one element from this family, right? So therefore, K belongs to this union, yes? And from the other side, when we have the elements of this union, any O, Si of O and Sj of O do not intersect, yes? And for any I and J, I draw boldface letters for multi-indices or for tuples in Q rho. Si of O intersection Sj of O is empty. So very nice family. Because if we consider this family, then its images under this family cover the whole row, and at the same time the images of the open set do not intersect. Please notice one fact, that K belongs to the closure of the open set. Why this is so? You would ask me why this is so. You see, S1 union Sm of O, Sm of O lies in O, right? When we come to the closures, it happens the same way, yes? Yes. Therefore, the iterations of O converge to K, and you see, so if I write this operator as T, we have T of O belong to O, so O contains T of O, and Tn of O converge to K, right? Therefore, each of these sets contains K. One second. What? Oh, we have a break in 15 minutes, right? Okay. Because I am adapted to 45 minutes, then break, then 45 minutes. So as 45 minutes are finished, I feel that I need to make a break. But it is a wrong feeling. So we defined this family QRO, and we established its very nice properties. So we keep in mind the K satisfies the open set condition, and this open set condition, when they are grouped in such families, images of the open set, when they are grouped in such families, are very well manageable. Yes, because they are almost of the same size, do not intersect, but their closures in common cover the whole K. Of course, if the contraction ratios are equal, such as in Sierpinski gasket, then there is no problem. We just take the copies of nth order, and all they are good. Yes, but if the copies have different sizes, then we need to make changes. There is one more model which is used in while we manage the self-similar sets. It is the following. So we have a projection of the index space to K, right? It's a address map. We considered the address space, yes, the space of infinite sequences, and we introduced a matrix on it. And this matrix turns the index space to a compact self-similar set. If this matrix coincides, the coefficient defining this matrix coincide with the Q1, Qm, then this self-similar set have the same similarity ratios as K, but with only difference that copies do not intersect. It is very well organized, yes. But I suppose I need to install or define an S-dimensional measure on this set of infinite sequences. How we measure? So you know that if we have I infinity, it is the union of sigma 1 of I infinity, sigma 2 of I infinity, and sigma n m of I infinity, where sigma of I1, sigma k of I1, I2, I3 at infinity, so it is a k I1, I2, I3. So sigma k is the operation which puts number k in the very beginning of the sequence. Yes. So I infinity is disjoint union of these sets, and these sets are usually called cylinders. Yes. And for any n, I infinity is a disjoint union of sigma I1 In of I infinity, right? So, for example, if I is equal to 2, we have sequences of symbols 1 and 2. Yes? So, this set is divided into two parts. One part is a set of symbols beginning with 1, and the second part is the set of symbols, symbolic sequences beginning with 2. Yes? But it can be also subdivided into the 1 I infinity, union 1 2 I infinity, union 2 1 I infinity, and union 2 2 I infinity. Sorry, do I speak sufficiently loud now? No? Yes? Because I begin to speak in very 2 to I infinity. Yes? So we have a sequence of how to key. So a sequence we take I infinity and divide it in several parts, then divide. So we have a sequence of subdivisions of I infinity, which such that diameters of these elements of this subdivision turn to 0. Therefore, we can define the measure of I infinity in the following way. So you have I infinity and it is divided in several parts, then it is divided in several parts. If we define the measure of each of these subdivisions, then we define the measure of I infinity. Yes? Because any set can be, any open set here can be represented as a union of such cylinders of different size, yes, and this will be always a disjoint union. So the measures of these cylinders will sum up to the measure of A. Okay, so we define the measure on I infinity in the following way. If we define a measure of each cylinder, then it's okay. So we have the system S1 SM. As far as I remember, we consider the system S1 SM. Yes? And the elements, the contraction ratios of these similarities are Q1, QM. And the sum of Q1 to the power of S, Qm to the power of S equals 1. right? Therefore, and for any n qi1 in, the sum of qi1 in to the power s also equals 1. We proved it. Very good. Then we have I infinity, and we define a measure on it the following way. The measure of sigma I1 in I infinity will be equal to qi1 in to the power of s. So we divided I infinity to m parts, and the sum of measures of these parts equals 1, yes? And then each of these parts is divided in m parts, and the sum of their measures is the measure of this whole part, yes? So we get a probability measure of I infinity, yes? Do you feel any kind of protest against my words now, Vijay? We have 5 minutes till the break. So we define the probability measure, and it is a natural measure. Yes, because the measure of each cylinder is the following one. So it's very good. It's very good measure. It is self-similar, because when we apply a similarity with ratio q, then the measure is diminished q to the power of s times. Okay. So it is a natural measure on I infinity. Yes, it is natural. Then so I take this I infinity with its natural measure and project it to k. So I have I infinity supplied by the measure mu, and I have a projection pi of I infinity to k. Yes. If we map one set to the other, and the first set contains some measures, so this measure is projected to the other set. So then we defined, if we have some subset, then the measure, so it will be the measure mu with this wave. Mu of A is equal to the natural measure of its preimage under pi. Mu of pi minus 1 of A. So, and this will be also a very good measure on A, because it will be self-similar with respect to the system S. You see that mu of Si of A will be equal, so not equal, because there will be overlap between copies. So it will be more or equal than qi to the power of s, multiplied by mu of A. So we defined a very special measure, which is the image of a probability measure on I infinity, and we put it on our set K, and we will use this measure we'll try to apply mass distribution principle to this measure. Yes. Okay. And it will be after the break. One question, sorry. Who